Today's video is Core Practical 16, the final of the core practicals, determining the value of an unknown mass using resonant frequencies of known masses. And Edexcel say that this is sort of like an investigation to finish it all off. So it's refreshingly straightforward. What you're doing is you are adding a range of masses onto the end of a spring, setting the spring in oscillation, and then timing those oscillations. What you're trying to figure out is you're trying to figure out the relationship between the time period of the oscillation and the mass, with the eventual view to using the time period to determine an unknown mass. This is your setup, very simple. Take a retort stand and you hang a spring from it, and then just hang those masses from the spring, and obviously you need a stop clock too. There's a bit of a risk assessment that goes along with this. You obviously have to look after your feet and make sure that the masses don't fall off the spring onto your feet. You'd be advised to clamp the retort stand with a G-clamp to the bench as well, because as the masses increase, you're going to get some turning effect and it might fall over. And the third thing they say, it's not quite a risk assessment, but don't overload the spring. If you overload the spring, you may go past its elastic limit and the experiment will become invalid. The relationship that governs this experiment is this one. T is equal to 2 pi root m over k. That means that t is proportional to root m. And you can base your experiment on that, or t squared is proportional to m. Because of course, you square both sides, you get t squared is equal to 4 pi squared m over k. K being the spring constant, that means we end up with t squared is equal to 4 pi squared over k times m. And of course, that is y equals mx. So you plot your masses on the x-axis, t squared on the y-axis, and because all of these are constant, you should get a straight line, and it should pass through the origin. So what we're going to do then is, because this is our independent variable, we are going to change the masses, and then we are going to time the oscillation. So we want the time period. Now, there's a couple of things that we need to think about here in terms of the accuracy of our experiment, and so we'll look at those now. There are a couple of standard ways throughout A-level physics that you can improve your accuracy, and measuring something longer is always one of them, because that is going to reduce your percentage uncertainty. So in this case, we're not just going to measure the time for one oscillation, we're going to measure the time for 20 oscillations 3 times, and then divide that by 20 to get a value for t. And of course, you do it 3 times and you take an average, and it's that average that you divide by 20. Now, the repeating and averaging is obviously a great way of improving your accuracy, because it reduces the effect of random errors. Now, a lot of people get this wrong and they say it reduces random errors, but of course it does not. The random errors are still there. That's the nature of them. But what you want to do is you want to mitigate them a little bit, so that when you take an average, it smooths out any slight increases or decreases that might be there. So reducing the effect of random errors is the purpose of taking an average. And here is some sample data. You can see that the mass is measured up to 0.7 kilograms. And I've just put in the average of the 20 T's here. You'd obviously have to have 3 columns for your 3 repeats. There's the average. I've divided that average by 20 to give me this number. And note, I've kept the number of decimal places because we're still talking about a time here, and your timer would have 2 decimal places. It would time to 100th of a second. And so you keep the decimal places here. And because I'm on 2SF for my time squared, therefore, is kept on 2SF. So what you do is you change the masses, start with 0.1, measure 20t, do that 3 times, find an average, and then increase it to 0.2, and so on. And then at the end, you have this unknown mass. And what you do is you then measure the time period, again 20t, do it 3 times, find an average for your unknown mass, and you're going to use the graph of your t squared against m to figure out what the unknown mass's mass is. And here's the graph of the data above. I've done it on Excel. It's probably better in this case to do it by hand, because you need to read off exact values on your scale. But here it is. You'll note that it does not go through the origin, so we clearly have some form of systematic error here. But it is a straight line. This, at some point you may be asked to explain why this is. Why are all of our time periods greater than they should be? Because of course this line should be slightly lower than it is. That could be due to a reaction time error. So our unknown mass time was 0.560 seconds. And so its t squared is 0.314 seconds. So what we need to do is we need to find, and again, a hand-drawn graph will make this much easier. You need to find 0.314 seconds on your y-axis, somewhere in here, and then go across and go down and find out what the mass is, and then you take your unknown mass, put it on a scale, and compare the mass you got from your graph with the mass on the scale. Now, if you know you've got a systematic error, you can always subtract that from your t squared, because presumably you'd have the same systematic error in your t squared for your unknown mass, and therefore you can adjust for that. The idea is that you take this value here and compare it to the value on the scale and find out what your error is. And of course your percentage error, what used to be called the percentage difference, is the difference between the two over the value from the scale. Because of course that would be the true value times 100. The final question for us to answer is, would technology actually improve this experiment? You can certainly do it with technology using a position sensor, which is basically an ultrasonic sound sensor that will detect the position of the mass. As it goes up and down, you can then get a graph of its position against time and see the time for one complete oscillation or for 10 oscillations. It's unlikely, however, that this is going to significantly improve your accuracy, because with 20 oscillations or 10 oscillations, the percentage uncertainty that you're going to get is actually pretty small. And this is unlikely to give you much less of a percentage uncertainty. So while you can certainly do it, it adds another layer in, because you have to look at the displacement time graph and figure out the time period from that. And it's not really going to give you a significant benefit.